First, let me note that I labeled this time constant here R over L because I simply wasn't thinking. The constant should be L over R. So I've got R over L here. It should read L over R. And the reasons for that will be very obvious once we do this. And over here, same thing. This R over L should have been L over R. So I'm going to make that correction off the camera here. Okay, made the correction. L over R is the time constant, and L over R occurs here as well, and we'll see that in just a minute. And we also have, of course, the half-life. Now, I don't know what happened to my labeling here, but something did, and I'm going to have to fix that. Okay, we have Imax here, your maximum current, and that turns out to be just V over R, and 1/2 Imax here. And as we've seen previously in relation to RC circuits, the time required for the current to exponentially approach its asymptote is called the half-life, and it's the time in which it takes the current to go from 0 corresponding to closing the switch on an LR circuit with constant voltage from 0 to half the maximum current. And then the time constant L over R is the time it takes to fall to 1 over E times Imax. I didn't label that, but that's again analogous to what we've already seen with RC circuits. So we have the half-life here, the time constant here. The half-life, as we'll see in a minute, is about 0.7 times the time constant. Make sure we've got that labeling. Okay. Well, the time constant, and I didn't fix this one, is L over R, not R over L. So we'll let that dry as we talk, but this is L over R. And the reason for that is if we have the function 1 minus e to the negative R over L times t, ignoring the sub h here for a minute, then if t equals L over R, we get e to the negative 1. And when we get e to the negative 1, well, that's 1 over e, and you can verify just basically using your pre-calculus understanding of exponential functions that that's the time it takes for the function to fall to within 1 over e of its asymptotic value. Now, what we want to find is the half-life. TH is going to be the half-life, so I probably ought to notate that here. And in a half-life, your current is approaching 1/2 of the maximum. The maximum is V over R, because when you have an RL circuit, when you reach maximum current, then there's no more change in current, so that there's no back EMF from the coil or the inductance element, and you're just running the voltage through the resistance, and you end up with current V over R. Now, 1/2 V over R is going to be the current when you've fallen to half, when you've risen to half of your max. So that we have this equation for T sub H, the half-life. And the equation is very, very easily solved. We distribute the V over R, and then we subtract V over R from both sides to get negative V over R e to the negative R over L times TH, and that's equal to 1/2 V over R. And then we simply divide by negative V over R. We get e to the R over L times TH is 1/2, which means that R over L times TH is the negative log of 1/2. And I've skipped a step there, but we take the log of both sides. We get negative R over L times TH equals natural log of 1/2. And the natural log of 1/2 is about negative 0.7, the negative of that being then approximately 0.7. And it follows then, if we solve for TH, that we multiply by L over R so that TH equals L over R, 0.7 times L over R. And that's what we have up here. Really bad looking T there, but that's a T sub H, is approximately 0.7 L over R, not R over L. Again, I wrote that without thinking and without checking out the units. Okay, so that's always a bad idea. Anyhow, and then we bring that up here, and that's then approximately to 0.7 times 3 seconds or 2 seconds. And we did calculate the time constant L over R by plugging in the given resistance, 10 to the 4th ohms of the 4th problem. Should have mentioned this is the 4th problem on the document. And we divided that by the 3 times 10 to the negative 5th henries. And you can check out the units, and it would be a good exercise to do that. You get 3 seconds, approximately 3 seconds, ballpark, 3 seconds. The 3 here should actually be a little higher. And that probably gets us closer to 3 seconds than we'd be just using the 3 here. Okay, well, gives us our half-life. Now, we want to think about this intuitively. What did we do in lab where we were able to observe the rate at which the function approaches its asymptotic value? Well, we had an RC circuit that we set up with a square wave. You start with 0 current and 0 EMF, and you apply some voltage, and that voltage gives you the current that you're going to approach. Current that you're going to approach. You set up circuits where the approach, by adjusting the resistance, you got an approach to the asymptotic value that took a few seconds. Okay, so the idea that we could get halfway to this value in 2 seconds is not foreign to you. Now, we want to go on and use this idea to figure out how much energy there is stored in that inductor when you get up to full current. So we'll talk about that in the next clip.